In this video, I will derive the last geometric series formula that you encounter on finite impulse response filters that you'll be using. And the example that I will be using concerns the moving average. And I talked about this in an earlier video, so this can serve as a review as well. In the earlier video, I derived a summation of a finite sequence consisting of bk terms going from k equals 0 to m minus 1. And we develop a closed form formula given here. I'll derive a more general case. Instead of doing k starting from k equals 0, we start from k equal to n1, ending at n2. So we replace the m minus 1 here, the upper index, with n2 for this second formula. So we're trying to develop a closed form formula for this case, which is more general than the one here, although this formula you encounter frequently when you hit finite impulse response filters as well. So once again, we're going to take the summation of a finite sequence going from n1 to n2, where we have these terms, and we're going to add them all up and develop a closed form formula. As before in the earlier video, this infinite series of the summation can be reduced to this simple formula of 1 divided by 1 minus beta. We also have this constraint here that the absolute value of beta is less than 1, and again that's for stability purposes when we're going to hit finite impulse response filters and sequences. We take this equation right here and we're going to multiply it by a term. In the first case, we're going to multiply it by beta raised to the n1 power. So on both sides of this equation. Okay, here and here. So here, for these series of terms, every exponent here is going to be increased by n1. So the first term with a 1 is just going to be simply beta n1 multiplied by 1 gives us a beta n1 for the first term. The second term is just going to be simply we're just going to simply take this exponent of 1 and add n1 to it. And then so on with the second term where we add n1 as well, and so on down the line. Also note here, since n1 is less than n2, I also included n2 here and here. And again, this is an infinite series, but we know that n2 is less than infinite as well as n1, and so I included these terms as well. So that's the series terms here, and the closed form solution to this infinite series becomes where the numerator just beta raised to the n1 power. Now we're going to take this same infinite series expressions and multiply it. Instead of beta raised to the n1 power, we're going to multiply it by beta n2 plus 1 power. So here, every exponent here is raised by n2 plus 1. So the first term just simply is just beta n2 plus 1. So we just raise that power by n2 since the exponent of this is 0. And here, beta is raised by 1. So that leaves, adding up the exponents, n2 plus 1 becomes n2 plus 2. And that goes with the rest of this series of terms that goes on all the way up to infinity. So that's the right side of this equation of these terms, and the closed form solution for this infinite series now becomes beta n2 plus 1 divided by 1 minus beta. Now we're going to subtract this term from this expression, and what we have is cancellations where anything that's higher than n2 gets canceled. So all these terms that are higher than beta over n2 plus 1 gets canceled from the subtraction, and what we're left with is these collection of terms, and which is just simply the summation from n1 to n2. So our closed form formula from going from summing up these bk terms, b raised to the kth power, going from n1 to n2, is simply this formula here, beta n1 minus beta n2 plus 1 divided by 1 minus beta. Now we're going to apply an example in using this formula. So here we'll have a beta of 0.8, n1 will equal 2, and n2 will equal 4. Substituting these values into this closed form solution, 0.8 raised to the second power minus 0.8 raised to the fifth power, because when you substitute 4 into here, that gives us 5. And we divide all that by 1 minus 0.8. The final result for this calculation is 1.5616. Now we'll do it the long way, adding up all these terms, and it turns out to be exactly the same answer as this one here. So this hopefully gives you more confidence in how do we apply this formula. Now if we take this formula that I just derived and compare it with the one I derived in an earlier video, we see that this one is a special case that I just derived. Here k is equal to 0 for n1, so that leaves this term here in the numerator equal to 1 since it's raised to the 0 power. And then the upper index is simply equal to m minus 1 here is equal to n2. And solving for m is just n2 plus 1. So we see here the second term in the numerator are basically equal. So this formula here derived in the previous video is a special case of the one I just derived. As a way of review, I'm going to take this formula here, which is the specialized case that I just derived in an earlier video, where the lower index is equal to 0 and the upper index is m minus 1, and use this closed form formula and apply it to a 7-point moving average, which is also an FIR filter as well. So basically, the 7-point moving average is simply taking 7 input values and averaging it to get our output. So it's basically a smoothing type or low pass filtering operation. We're going to specialize it for the case when the input is a complex exponential, defined here as e to the minus j omega het n, where omega het is the normalized radian frequencies used in discrete time systems and signals. I rearranged this term here, factored it so that we can isolate e to the minus j omega het and define that as beta, so we can see that this moving point average can be formulated with this closed form solution. So we simply just apply the formula here for this case. So when we do this, substituting for beta here, we have e to the minus j het raised to the 7th power, or simply e to the minus j 7 omega het. And then just the denominator is just simply replace the beta with e to the minus j omega het n, and that's shown here. Now I'm going to take this expression and put it in a more common form found in most DSP or digital signal processing books. So what I'm going to do is a little bit of algebraic gymnastics in which I take the exponent here in the numerator and here in the denominator and factor half of the exponent out. The reason why I do this is because we're going to get a form of Euler's equation here, e to the j minus e to the minus j, and if I divide in here in the numerator by 2j, I get a sign identity. And then I do the same thing, divide by 2j in the denominator, and I get some type of sign identity here as well. So what I do is I take this exponent, factor half of it out, giving us 7/2 omega het. Now, did I change anything in the numerator? No, because when I multiply e to the minus j 7/2 omega het by e to the positive j 7 omega het over 2, these exponents add up to 0, giving us 1. And then when you look at this second term here and multiply it by minus j 7/2 omega het, that just simply gives us negative j 7 omega het. In the denominator, we'll do the same thing. We factor half of the exponent, giving us e to the minus j omega over 2. And we have the same type of form we have in the numerator, where we multiply this term and this term, and the exponent adds up to 0, giving us 1. And that half omega het with a negative sign here and a negative sign here, another half of omega het, gives us e to the minus j omega het. So the numerator here for this expression gives us a sine 7 omega het over 2. This is using Euler's identity or formula. And the denominator gives us the same thing as well. Now, here we have e to the minus j 3 omega het, and that's due to an algebraic addition of the exponents. We'll see later that this expression here, e to the minus j 3 omega het, is simply a delay operator in which is shifted. Okay? But that comes much later in the future where I discuss this part. Okay? Just think of this as a delay term or a phase shift. So that's it in terms of how we apply this formula to a 7-point moving average. So here's a plot of this equation that we just derived, and we put it in this form because we can see where the zeros of this graph occurs. All right? It occurs when the numerator is equal to 0, and that's when the sign is equal to 0, which are integer multiples of pi. And we'll see that this plot acts like a low-pass filter, but this will be discussed in future videos. Signing off is Dr. J.